In the last chapter, we walked through every planet in the solar system and looked at exactly how each one tries to destroy our spacecraft. Mercury cracks them apart with thermal shock. Venus crushes them in minutes. Jupiter cooks their electronics with radiation. Saturn's rings would tear them like a shotgun blast. It was a list of failures, a list of reasons not to go. This video is the opposite, because for every one of those death traps, engineers have already started designing the answer. Some of these technologies exist today, sitting in research labs. Others are blueprints on paper. A few are still science fiction, but all of them are real attempts to solve real problems. And together they sketch out the only realistic path humans will ever take to colonize the worlds around us. This is how we beat the solar system at its own game. Mercury's defining problem is the day-night swing. Surface temperatures climb to roughly 800 degrees Fahrenheit in direct sunlight, then drop to about minus 290 degrees Fahrenheit in shadow. Most engineering materials simply can't survive that. Metals expand when heated and contract when cooled. After enough thermal cycles, joints fatigue, seals fail, and structural components fracture along grain boundaries. So how do you build something that lives through that without falling apart? The first answer is a category of materials called shape memory alloys. These are metallic compounds, typically nickel-titanium based, that can deform under stress and then return to their original geometry when heated. Instead of resisting thermal expansion the way conventional metals do, they absorb the deformation and reset. That's not theoretical. NASA has already used shape memory components in landing gear tires and deployable mechanisms. Scaling that approach to full spacecraft structures is one of the active research directions for any future Mercury surface mission. The second answer is reflective shielding. Mercury sits close enough to the Sun that solar radiation hits the surface at roughly 11 times the intensity it does at Earth's orbit. The trick is not to absorb that energy, it's to bounce it. Advanced ceramic mirror coatings, similar to those being tested on the Parker Solar Probe's heat shield, can reflect over 99% of incoming solar radiation. A Mercury habitat would be wrapped in those, with the reflective surface always facing sunward. And the third answer is geography. Mercury has permanently shadowed craters at its poles, where direct sunlight has never reached the floor. Inside those craters, temperatures stay stable and water ice has been confirmed by orbiter observations. A future settlement wouldn't fight the surface conditions. It would tunnel into the crater walls and use the regolith above as natural insulation. Several feet of compressed lunar-style regolith blocks both thermal extremes and radiation simultaneously. The colony lives in shadow, draws water from the ice deposits, and lets the planet do the shielding for free. Venus is the worst surface environment in the solar system. Atmospheric pressure on the ground is 92 times Earth's, equivalent to being roughly 3,000 feet deep in the ocean. Surface temperature sits at 900 degrees Fahrenheit, hot enough to melt zinc. The cloud layers above are made of sulfuric acid, which corrodes most exposed materials and seals in seconds. Every Soviet Venera lander we've ever sent down survived for less than 2.5 hours before being silenced. The conventional approach is to harden everything, build thicker, cool faster. That doesn't work. Cooling systems on Venus have nowhere to dump waste heat. The air around them is hotter than the inside of the spacecraft. Refrigeration runs in reverse. The real solution is to redesign the electronics from scratch. NASA Glenn Research Center has already built and tested working circuits using silicon carbide instead of conventional silicon. Silicon carbide chips operate continuously at 932 degrees Fahrenheit without any cooling system at all. They simply don't need one. They tolerate Venus's surface temperature as their normal operating range. Prototype SiC sensor packages have already run for over 60 days inside a Venus simulation chamber at NASA Glenn, the Greer chamber, without failure. That's longer than every Venera mission combined. Then there's the pressure problem. Instead of building a rigid hull thick enough to resist 92 atmospheres of crush load, the new approach is a bellows-style structure made from titanium. Imagine the design philosophy of a deep-sea bathysphere combined with an accordion. The vehicle compresses slightly under load instead of fighting it. distributing stress across many flexible joints rather than concentrating it on rigid weld seams. The same principle is used on submarines that operate at extreme depth. And for human presence, the most realistic plan doesn't involve the surface at all. About 30 miles above Venus, atmospheric pressure drops to roughly Earth equivalent and temperature settles around 80 degrees Fahrenheit. NASA's HAVOC concept proposes massive Teflon skin dirigibles floating at that altitude. Teflon resists sulfuric and corrosion almost completely. Crew quarters would be suspended below the envelope. The colony floats in the cloud layer, drawing energy from sunlight. Venus has plenty of that, and pulling water and CO2 directly from the surrounding atmosphere for life support and propellant. Mars looks survivable from a distance. Average temperature around minus 80 degrees Fahrenheit, a thin CO2 atmosphere, regolith you can stand on. Compared to Venus, it's a vacation. It's not. Mars has two specific killers, and both required completely new engineering categories to solve. The first is dust. Martian dust isn't like Earth dust at all. It's electrostatically charged. Every grain carries a slight electric charge from UV exposure and friction in the wind. That charge means it sticks to every surface it touches, especially solar panels and spacesuit fabric. NASA's Opportunity rover survived on Mars for 15 years before a single dust storm in 2018 coated its panels thickly enough to cut off all power, and the rover died. The fix being developed at NASA Kennedy is called the Electrodynamic Dust Shield, or EDS. It's a thin, transparent grid of electrodes embedded directly into solar panels and spacesuit visors. When activated, it generates a traveling electric field across the surface, essentially a moving wave of polarity changes that physically pushes charged dust particles off the panel. Lab tests at Kennedy Space Center have removed over 99% of accumulated Mars stimulant dust within minutes of activation. EDS hardware is scheduled to fly on the Lunar Surface Innovation Initiative as a precursor demonstration before being deployed at Mars. The second killer is radiation. Mars has almost no magnetic field, so cosmic rays and solar particles reach the surface unimpeded. Daily radiation dose on the Martian surface runs about 40 times what an astronaut absorbs on Earth. Over a typical 500-day surface mission, that accumulates into a serious cancer risk. The leading solution doesn't involve building thicker spacecraft. It involves moving underground. Mars has confirmed lava tubes, natural tunnels carved by ancient volcanic flows, some of them hundreds of feet wide and miles long. Orbital observations from Mars Reconnaissance Orbiter have already imaged collapsed entrances to these tubes, called skylights. Several feet of basalt rock above a habitat blocks essentially all cosmic radiation. The European Space Agency and several NASA proposals now treat lava tube colonization as the baseline plan, not an alternative. The first crewed surface base will likely be inside one. Soil contamination is the third issue. Martian regolith contains percolates, chlorine-based salts that are toxic to humans and to most crops. Any agricultural project, like the potato farm in the Martian, would need to remove them first. Bioremediation using engineered bacteria that metabolize percolate into chloride and oxygen has been demonstrated in lab settings on Earth. The same bacterial cultures could be transported to Mars and used to detoxify soil for greenhouse use. As a bonus, the process releases breathable oxygen. Jupiter's magnetic field is 20,000 times stronger than Earth's, and it traps charged particles into radiation belts so intense that an unshielded human would absorb a lethal dose in less than a day. Standard electronics fail in hours. Even hardened spacecraft systems degrade rapidly with each pass. NASA already solved this one partially. The Juno spacecraft has been orbiting Jupiter since 2016, and it survives because its critical electronics live inside a 400-pound titanium vault. 1 cubic foot armored box at the center of the spacecraft that blocks the worst of the radiation. The processors inside that vault are also radiation hardened, designed specifically to keep functioning when individual transistors are getting struck by high-energy particles. For future missions, the next step is layered shielding. Titanium handles high-energy particles, but it's heavy and it generates secondary radiation when struck. The new approach pairs titanium with polyethylene, a hydrogen-rich plastic that absorbs neutron radiation without producing dangerous secondary emissions. A multi-layer shield of metal plus polymer plus water tank gives much better protection per pound than any single material. Then there's the orbital strategy. Juno doesn't fly through Jupiter's radiation belts continuously. It flies a highly elliptical orbit that spends most of its time far from the planet, making fast, close passes near the poles where the belts are thinnest. The total radiation exposure is dramatically lower than a circular orbit would deliver. Future missions to Europa, the most promising moon for finding extraterrestrial life, are planned the same way. Quick scientific flybys, then retreat to a safer distance to dump data and recharge before the next pass. And for the deepest exploration, atmospheric probes that drop into Jupiter itself, the answer might be sacrificial swarms. Instead of one large, expensive lander, fleets of small, cheap probes drop simultaneously, each transmitting until destroyed. The mission cost per probe drops, the total data return goes up, and we lose individual probes without losing the mission. The Galileo atmospheric probe in 1995 was the first attempt at this. It descended for 58 minutes before being crushed. The next generation will be a coordinated swarm rather than a single vehicle. Saturn, Uranus, and Neptune share a single dominating problem. They're far. Saturn is roughly 886 million miles from the Sun on average. Uranus is 1.8 billion miles out. Neptune is nearly 3 billion miles away. With current chemical propulsion, those journeys take 7 to 15 years one way. Spacecraft systems degrade, funding cycles end, engineers retire before the mission arrives. The fix is propulsion. NASA and DARPA are jointly developing a nuclear thermal propulsion system called DRACO, Demonstration Rocket for Agile Cislunar Operations, which uses a small nuclear reactor to heat hydrogen propellant to extreme temperatures and expel it through a nozzle. The result is roughly twice the specific impulse of the best chemical rockets ever built. A nuclear thermal stage could cut a Neptune mission from 12 years to under 5. The first DRACO test flight is currently scheduled for 2027. The second problem is wind. Neptune has the fastest atmospheric winds in the solar system, peaks of 1,200 miles per hour, which is faster than the speed of sound at sea level on Earth. Conventional probe designs use parachutes to slow descent, but parachutes get destroyed at those speeds. The next generation of atmospheric probes use a bullet-shaped aerodynamic profile designed to ride the winds rather than fight them, slowing through atmospheric drag alone over a longer descent path. The third problem is communication delay. A radio signal from Neptune takes over 4 hours to reach Earth. Real-time control is impossible. If a probe encounters an unexpected wind shear or a fault, it can't ask Houston what to do. By the time mission control hears about the problem and answers, the probe has already crashed or has been destroyed. So the autonomy stack has to be on board. Modern spacecraft AI systems make navigation, fault management, and even scientific targeting decisions independently. Perseverance already does this on Mars at smaller scale. Its terrain relative navigation system selected its own landing spot in real time during descent. Outer planet probes will need orders of magnitude more autonomy than that. There'll be self-flying scientific platforms making judgment calls about what's worth photographing and what's worth abandoning, all without checking in. And one bonus, because the deeper we go, the colder it gets, Pluto's surface temperature averages around minus 380 degrees Fahrenheit. At that temperature, batteries fail, lubricants seize, solar panels are useless because the sun is just a bright star at that distance. Sunlight at Pluto is roughly 1/1600th the intensity it is at Earth. The only working solution is nuclear power. Radioisotope thermal electric generators, RTGs, convert the heat from decaying plutonium-238 directly into electricity. The Voyager probes have run on RTGs since 1977 and are still transmitting data nearly 50 years later. New Horizons made the Pluto flyby on the same technology. Next-generation RTGs being developed at the Department of Energy and NASA Glenn will be more efficient and longer-lasting, with operational lifetimes potentially exceeding 100 years. Those are the engines of any future outer system mission. Without them, we don't go. None of this is about brute forcing nature. Every solution we've covered shares the same underlying principle. Don't fight the environment, match it. Mercury's thermal cycling breaks rigid materials, so we use alloys that flex with the heat instead of cracking. Venus's pressure crushes rigid hulls, so we build bellows that compress and recover. Venus's heat destroys cooling systems, so we design chips that don't need cooling at all. Mars' dust sticks to surfaces electrostatically, so we use electric fields to push it back off. Mars' radiation passes through walls, so we move underground where the planet itself shields us. Jupiter's belts overwhelm shielding, so we make fast passes instead of slow ones. Neptune's distance defeats real-time control, so we build probes that decide for themselves. The pattern is consistent. The worlds around us aren't going to become less hostile. We're the ones who have to change. And the wild thing is, almost everything in this video is technology that exists today, in some form, in someone's lab. Silicon carbide chips have run for 2 months in a Venus chamber. EDS prototypes are removing 99% of dust under simulation. The Draco reactor is on the launch manifest. Layered radiation shielding is in active testing for the Artemis program. The Moon is the proving ground. Mars is the first deployment. After that, Venus, Mercury. The outer system opens one engineering breakthrough at a time. Survival isn't about being tougher than the environment. It's about being smarter than it. Of course, none of these solutions matter unless you understand exactly what we're up against. If you haven't seen the first part of this story, the one where every planet in the solar system tries to destroy our spacecraft in a different way, that's the video that explains the actual threats. Watch it here and you'll see exactly why every technology we cover today had to exist in the first place.